Hello and welcome to the Unit 4 podcast on section 11.3, moles of compounds. I'm Mr. Sakaguchi.
Which makes me Mr. Lin.
And let's start. So we talked in the last podcast about moles and masses of atoms. So now what we want to do is we want to relate this to compounds because moles of atoms make up moles of compounds.
So this time we're going to be linking up the previous concepts with a whole molecule or an entire set of formula units. Okay, and these can get kind of large, but the math is easy to follow through on. Okay, so let's take a look at a breakdown of a basic molecule here, where we've got CCl2F2, and remember that what this means is that there's one atom of carbon, two atoms of chlorine, and two atoms of fluorine. Right? So that we can look at it as saying that 1 mole, where's the arrow? There it is. 1 mole of this compound, of this molecule, should be made up of 1 mole of carbon, 2 moles of chlorine, and 2 moles of fluorine. All right? So if we've got 5.5 moles of this molecule, 5.5 moles, and you follow through on how many molecules of carbon there would be, we'd have 5.5 moles of carbon, 11.0 moles of chlorine, 11.0 moles of fluorine due to the ratios from the compound. It was in a 1 to 2 to 2 ratio, so we've got a 1 to 2 to 2, and we just keep multiplying it by the 5.5.
Yeah, so the important thing to note here is that we can relate moles to, they're directly relatable to atoms. Okay, so that's one thing to kind of keep in mind because there will be some instances where we're interested in the amount of an individual atom within a compound. Molar masses of compounds are also treated treated slightly differently than moles of atoms. If we want to know how much a mole of a compound weighs, what we have to do first is break down the compound into its atomic components. Then what we do is we go and we refer to the periodic table and we find the molar mass of each of the atoms. And then if there happens to be more than one type of atom in a formula, it gets multiplied by its corresponding subscript, and then we sum the masses.
All right, so in this example, we've got 1 mole of Ca3PO42, calcium phosphate. So we've got 3 calcium atoms, 2 phosphates, because it's 2 times the 1 phosphate, and 8 oxygen, because of 2 times 4. Right? And then we find the individual elements and their masses and multiply and add together. So we've got atomic mass of calcium is 40, so it's 3 times 40. Atomic mass for phosphorus, 31, multiply that times the 2 for the ratio in the compound. And then atomic mass for oxygen, 16. These get multiplied and then totaled up together, completely summated, to get you 310 grams. And that 310 grams is for 1 mole of calcium phosphate. So a way to look at this is kind of like saying you can weigh the mass of 1 egg, or you can weigh the mass of a dozen eggs, right? And that dozen eggs is going to have the mass of 12 eggs in total. So that's all we're doing here. We're adding up the individual pieces together to get your total mass.
So let's say we were going to convert moles of a compound to mass. So let's say I gave you a problem like, you have 2.5 moles of glucose, C6H12O6, and I want to know how many grams that is. Well, if we look at our 2.5 moles, we know we're on the center of our mole road, and we want mass, which means I want grams, so I'm going to move down the street, which means I'd multiply by molar mass in grams over 1 mole. So the first thing I need to do is I need to go to the periodic table and figure out the molar mass of glucose. So if I take the formula for glucose and I break it down, there's 6 carbons, 12 hydrogens, and 6 oxygens. I go to the periodic table and I round these for carbon, hydrogen, oxygen to 12, 1, and 16. And when I multiply this, or I multiply each individual one and add them together, I get 180 grams for every 1 mole of glucose. Now I'm able to actually solve the problem. So I start with my given over 1. And I multiply by my molar mass over 1 mole. The moles cancels. I multiply through and divide, and that leaves me with 450 grams of glucose.
Now, the reason this is important is because scientists and yourself won't be won't be running experiments in terms of actual moles. Because we don't have a scale that measures moles. What we do have are scales that measure mass. So we definitely need to know how to convert from grams to moles, because the real world works in grams, but these chemical reactions work in moles. That's why we need to do this.
And that'll make a little bit more sense in future units when we discuss some chemical reactions. We can also do the reverse, where if I have a mass of a compound, I want to know how many moles there are. So let's say I have 325 grams of calcium hydroxide and I want to know the number of moles. Using the mole map, because I have 325 grams, I know we're in the mass part. We're the bottom part of the street, and I want moles, so I'm going to the middle part. And as I go from the bottom to the middle, I'm going to multiply by 1 mole over the molar mass. Now I need to figure out the molar mass of calcium hydroxide. So I find the mass of calcium plus 2 oxygens, because any number outside the parentheses multiplies in. So that's 2 oxygens and 2 hydrogens. I go to the periodic table and I find these values. So there's 40 for calcium, 16 for oxygen, and 1 for hydrogen. I multiply and add, and I end up with 74 grams per mole. I can then go ahead and do the actual problem. I start with my given over 1. I multiply by 1 mole over the molar mass, and since I have grams above and below, they cancel out. I multiply and divide, and I end up with 4.39 moles of calcium hydroxide.
Yep. So then it's also possible to extend our process. I mean, we've gone from mass to moles. We can also find out how many representative particles there are from a given amount of mass. So in the problem here, we've got 35.6 grams of aluminum chloride, and using the mole map, we want to figure out how many representative particles are in 35.6 grams. So again, with the previous step, we've got our ratio for the individual elements of 1 aluminum, 3 chlorine. We look up the periodic table for their individual atomic masses, so we get 27 for aluminum and 35.5 for the chlorine. You multiply and add and get your 133.5 grams per mole of aluminum chloride. Over 1, of course. Okay? And then since we're moving up from the mass position here, we're starting here, down here at the bottom, we're going to move up to moles first. It's not possible to jump straight from mass to representative particles. You have to go through the moles. So our first step will be 1 mole over the molar mass of 133.5 grams. That's our first multiplication. And then, of course, the grams are going to cancel out. And then after that, that gets us to our mole step. And now that we're at our mole step, we can move on to our representative particles, which would be Avogadro's number over 1 mole. All right, and then again, our moles will cancel out. And we follow through on the math, and now we have 35.6 times 6.02 times 10 to the 23rd divided by 133.5. That scientific calculator is looking real handy right now. When you finish up, you get your 1.61 times 10 to the 23rd formula units of aluminum chloride.
A couple other things to point out here is what we've been doing up until this point is what we would call a one-step conversion, where we're only multiplying by 1 fraction here. What we're doing here in this particular kind of problem is we're doing a 2-step calculation, where we're not multiplying by 1 factor but by 2. You can think of the mole as kind of like the middleman to go from mass to particles and back again. Okay, just something to keep in mind.
And we'll see you next time.